Hey everyone, and welcome. Today we're diving deep into one of the most powerful ideas in AI right now, fine-tuning. This is how you take a general do-it-all AI and turn it into a razor-sharp specialist. We're going to break down exactly how it works, so let's get right into it.
But first, let's talk about what happens when things go wrong. Really wrong. You've probably seen a story like this. Air Canada's chatbot literally invented a bereavement policy out of thin air, and a court actually forced the airline to honor it. It is the perfect and kind of painful example of why you can't always trust a general AI with a specific high-stakes job.
And that really gets to the heart of the matter, right? Why do these incredibly smart, powerful models sometimes just fail so badly? What is it about them that makes building a true reliable expert so tricky?
To figure that out, here's our game plan for today. We're going to start with the problem itself. Then, we'll compare the two main ways to customize an AI. We'll look at how fine-tuning actually works under the hood, explore the new methods that make it way more accessible, check out some mind-blowing results from the real world, and finally, lay out a clear path for how you can get started.
Okay, so first up, the problem. That one-size-fits-all model that we see everywhere, well, it has some pretty serious limitations that you need to know about.
The main issue comes down to a word you've probably heard a lot: hallucination. Now here's the key insight, the thing that changes everything. We tend to think of this as a bug, but it's really more of a feature. No, seriously, these models are built to predict the next most probable word, not the next most factual word. So making stuff up isn't a glitch, it's a fundamental part of how they operate.
So, if we want to get that under control and make an AI that's actually reliable for a specific job, we basically have two paths we can go down: prompt engineering and fine-tuning. Let's see how they compare. You know, the easiest way to think about this is like this. Prompt engineering is like giving really good directions to a taxi driver. You're just guiding the model. But fine-tuning? That's like sending that driver to a special academy to become an absolute expert on one single route. You're actually upgrading their skills. So prompting is cheap and flexible, but you'll hit a ceiling on accuracy. Fine-tuning takes more work, but it's how you get that top-tier, expert performance.
And the data makes this crystal clear. Just look at this research from IBM. Prompting, that's the blue line. It kind of levels off. It hits a wall. But model tuning, or fine-tuning, that orange line just keeps on climbing. The bigger the model, the bigger the advantage. The message is simple. If you absolutely need the best possible performance, fine-tuning is the way to go.
All right, so you're probably asking, how does this magic actually work? Let's pull back the curtain and see how you can teach an old model some brand new tricks. At its heart, the whole concept is actually really simple and elegant. You take a massive pre-trained model that already has a deep understanding of language and the world. Then you just keep training it, but this time you use your own small, super high-quality dataset of examples for the specific thing you want it to do, whether that's understanding legal contracts or writing in a certain style. And right about now, I can hear you thinking, wait a second, doesn't that cost an absolute fortune? Don't you need a warehouse full of supercomputers to retrain one of these giant models? And you know what? For a long time, the answer was a big, resounding yes. The killer was always memory. When you do a full fine-tune, you don't just need memory for the model's weights. You need a ton of extra room for all the math that happens during training, things called gradients and optimizer states. It adds up so fast that you could need 20 times the memory of the model itself, which put it completely out of reach for pretty much everyone. But then, a massive breakthrough happened. And this brings us to the modern era and a family of techniques called parameter-efficient fine-tuning. You'll hear it called PEFT. PEFT is the absolute hero of this story. The idea is so smart, it's almost simple. Instead of changing all billion-plus parameters in the model, why not freeze almost all of them and only train a tiny fraction? This slashes the computational cost and suddenly makes fine-tuning something that anyone can do. It's a total game changer. The most famous and popular PEFT method out there today is called LoRA, which stands for low-rank adaptation. The approach is just ingenious. It freezes all the original weights, and then, for each layer, it slips in a couple of really small trainable matrices. And this diagram just makes it so clear. See that big blue block? That's the huge original model. It's frozen solid. You don't touch it. Instead, LoRA adds this little side path, those matrices A and B. All the new learning for your specific task happens in this tiny, efficient little adapter, and the result just gets added to the main output. It's such a clever and elegant solution. Now, another really important technique is called instruction tuning. This is a special type of fine-tuning, where you're not just showing the model examples, you're explicitly teaching it how to follow orders. The data is literally pairs of, here's a command, and here's the perfect response to that command. And the real magic here is that you're not just training it on one single task. You can show it thousands of different types of instructions all at once. This is what teaches it to generalize, so it gets way better at understanding what you actually want it to do, even if it's never seen that exact command before.
Okay, so that's the theory, but what about the real world? Does this stuff actually work? Oh yeah, let's look at the proof.
You have got to see this. This is just incredible. A company fine-tuned a relatively small 7 billion parameter model just to pull data out of invoices. Okay, so the base model scored a 0.72. The mighty GPT-4o scored a 0.76, but their little fine-tuned specialist, it scored a whopping 0.88. It beat GPT-4o by 16%. This is just amazing proof of how powerful specialization can be.
But it's not just about getting the right answer. It's also about the style. Check out this LinkedIn post from a generic LLM. We've all seen this 1,000 times, right? It's corporate, it's safe, it sounds exactly like a robot wrote it. And now, look at the after. This is from a model that was fine-tuned on the unique, personal writing style of a real person. It's got an opinion, it's got a voice, it sounds completely human. This is a level of control over personality that you just can't get with prompting alone.
So what does this all mean for you? Well, here's a really practical 3-step playbook. 1. Always start with prompt engineering. Use a model off the shelf and just see how far you can push it. If you hit a ceiling and the accuracy isn't good enough, then you move to step 2, fine-tuning. And you probably only need a few hundred to a few thousand really good examples. And only for the absolute most difficult jobs do you need to think about step 3.
And this all leads to a really fascinating question about where AI is headed. As these incredibly powerful techniques get easier and cheaper for everyone to use, are we going to live in a world with just a few giant do-everything AI models? Or is the future going to be a vibrant ecosystem of thousands of tiny, specialized AI experts, each one a true master of its own craft? Definitely something to think about. Thanks for watching.